Let us continue the topic on synchronous motor. In this lecture, we will start our discussion on torque angle. From our previous lecture, we came to know that when we will provide a DC supply to the rotor of a synchronous motor, and there will be a three-phase AC supply to the stator side, then the rotating magnetic field and the rotor, they will be interlocked together, and the rotor will start moving with synchronous speed. Even though we increase the load on the motor, the speed of the rotor won't be decreased as long as they are interlocked. Now, what will happen if we increase the load? That will give us an idea on torque angle. If we draw this portion in zoomed view, the things will look like this. We have North Pole here. This is RMF, rotating magnetic field, and we have South Pole here. The fields are coming from north to south. Let's draw the axis line for the rotating magnetic field and the rotor point. So this is the axis line. They are on the top of each other. Suppose the rotor is made of without any load. That means we are considering the rotor is weightless. In that case, what will happen? These two axes will be on the top of each other. We have two axes here. One is for rotating magnetic field, which is centered at the middle point of the motor, and another axis is for the rotor case. Now, if we apply some load, or if we consider the weight of the rotor, they will not be moving having this axis on the top of each other's. Rather, there will be some angle deflection. How? Suppose this is the case. This is the rotating magnetic field, north RMF. Now, whenever the rotating magnetic field is rotating in this clockwise direction, if it has some weight in the rotor side, then fields will be interlocked. They will be moving together, but they will have some deflection. So this is the axis for rotating magnetic field, and this is the axis for rotor. This is the rotor. So in the axis of the rotor and the rotating magnetic field, this deflection is named as torque angle, and it is denoted by alpha. Now, if we increase load, this alpha value will be increased. If we decrease load, then this alpha value will be decreased. In practical case, this alpha value cannot be 0 because the rotor itself is a load for the rotor. The weight of the rotor itself is a load for the rotor. That's why we'll always get a deflection. So if the rotating magnetic field rotates in the clockwise direction, this rotor will also be rotating in the clockwise direction, but there will be some alpha angle deflection. This alpha angle deflection depends on the load. Suppose a higher amount of load is provided. So what will happen in that case? Let's see. This is the north pole for rotating magnetic field, and if we apply a bit higher amount of load, then the deflection will be like this. This is the axis for the rotor, and this is the axis for the rotating magnetic field, and the angle difference between them is alpha. Here alpha is higher. That means this motor is experiencing higher load than this case. So this is lightly loaded. This is highly loaded. Why this angle is called torque angle? Because the torque angle alpha depends on load torque. If we increase the load torque on the motor, which will eventually increase the produced torque, then in that case this alpha value varies. For increasing torque, alpha increases. For decreasing torque, alpha decreases. That's why this alpha angle is called torque angle. Next, we'll discuss on the equivalent circuit. equivalent circuit of a three-phase synchronous motor. Unlike induction motor, the synchronous motor is connected to two electrical systems. One is DC supply to the rotor and another is three-phase AC supply to the stator. Whenever we give a three-phase AC supply to the stator side and it creates a rotating magnetic field, in the stator side there will be a stator winding resistance which will cause the copper loss and the reactance due to the winding in the stator configuration. Now when we provide the DC supply to the rotor side and that creates a static magnetic field and this rotor starts rotating, suppose for the time being we forget about this rotating magnetic field. If we have north and south pole in the rotor side and this rotor rotates, this north pole will cut the windings and this south pole will cut the windings surrounded by this rotor. That means the stator winding. So the field that will come from the north pole and the field that will go inside south pole, both of them will cut the windings nearby. And we have winding configuration that is supplied from the three-phase supply. We have winding configuration here at 120 degree mechanically apart here and 240 degree mechanically apart here. So when this north pole cuts this winding, it's having the highest EMF, and after some time, after having some rotation, this north pole will come here and it will cut this winding with the highest value and south will come here. This will experience the opposite value. In this way, due to cutting of this magnetic field, EMF will be generated in each phase. That produced EMF will also be having 120 degree electrically apart, because if we provide a three-phase supply here that produces a rotating magnetic field which is static and rotating. Now if we think the opposite way, if we have a magnet that is rotating, that will also produce a supply or EMF in each phase that will have three phase in nature and they will be 120 degree electrically apart. This generated EMF, which is opposite to our supply EMF, is named as back EMF and it opposes the stator voltage. If we have supply voltage Vs, then the EMF that is produced by this rotation of this rotor magnet, that can be termed as EB. We are writing EB here, and this is back EMF. Remember, this magnitude of EB depends on the rotor flux, and this rotor flux depends on the magnitude of current, field current, IF. So if we increase field current, that means if we increase this DC supply to the rotor, that will eventually increase the rotor flux per pole, which will eventually increase the value of EB, back EMF. So the back EMF is produced by the rotor due to this rotation, and this Vs is given from the supply, this supply voltage, and this is the back EMF. They are opposite to each other. The value of EB also depends on the speed of the rotor, but since the speed of the rotor is always constant, that is having ns value, so we will consider that this magnitude of EB only depends on IF. Now the EB that will be produced here will be AC in nature, because sometimes north is here, south is here, and after some time south will be here, north will be there. So if we consider this wire is experiencing sometimes north side and sometimes south side, so it will produce a sinusoidally changing EMF. Supply is AC and the EMF that is produced as back EMF is also alternating in nature. Now another thing which I'll discuss again later on when I'll describe this equivalent circuit, but I want all of you to have some idea on that. If this north pole and south pole, they are aligned, if we consider there is no load in the rotor side, even we are ignoring the weight of the rotor, then they will be aligned. So the supply voltage and the voltage produced by the rotor will be on the same axis. There will be no angle deflection between Vs and Eb. But whenever there will be an alpha angle deflection, there will be a phase angle difference between Vs and Eb, and that will have a value equal to alpha. And obviously this Vs will be leading to Eb, because we can see when these two magnets are rotating, the magnet due to rotating magnetic field is leading than the magnet in the rotor side. So Vs leads Eb, or Eb lags Vs. Now let's draw the equivalent circuit. This is the per phase equivalent circuit that we are going to draw. In the stator side, we have stator resistance, reactance. This reactance is named as synchronous reactance. This is Ra. And here in the stator side, there will be a creation of an opposite EMF that is termed as Eb. So we are writing Eb, and this is the case. Here we have supply voltage Vs, per phase supply voltage, and current will be flowing through this stator line, and there will be creation of back EMF due to the rotation of this rotor, which rotates with a speed of synchronous speed. So this rotor can be represented by this circuit. Here we have VDC, that is the excitation, and due to this excitation some currents will be flowing, DC current will be flowing, and that magnet will produce this Eb. So ultimately this is the main part of the equivalent circuit. This Eb is the effect of the rotor rotation, and the magnitude of this Eb depends on the magnetic field or magnetic flux in the rotor side, which depends on this field current If. Also, it depends on the speed of the rotation of the rotor, and we will not consider the speed of the rotation of the rotor, because speed of the rotor in synchronous motor case, as we came to know, that it is constant ns. So the magnitude of Eb highly depends on the magnetic flux produced by the rotor. In other words, we can say on the excitation of the rotor. So this is the stator circuit, this is the rotor circuit, and that's it. This is the equivalent circuit of a synchronous motor. We can denote this current as Is, that is the stator current. Now we'll see what happens for different loading condition and different excitation condition on this motor, and how can we use the motor most effectively. If we know the theories, then it will be easier for us to understand the underneath principle of synchronous motor. From this equivalent circuit, we can write Vs is equal to Eb plus voltage drop in this impedance section. So we can write J Is XS plus Is into Ra. Now in synchronous motor, the value of XS is 10 to 100 times greater than the value of Ra. So the voltage drop in IaRa is very negligible with respect to this voltage drop in XS section. So we can neglect Ra unless we are interested in efficiency or heating effects. So this equation can be rewritten as Eb plus J Is XS. So this is the ultimate equation we are going to use for our further calculation. In another term, we can write Vs minus Eb equal to J Is into Xs. Here we need to consider the vectors. All these parameters are vectors. So the voltage difference between these two terminal will give us the voltage drop here, which is represented by Is into Xs. We can consider this value as ER. If we plot the vector, if we consider this is the supply voltage Vs, then Vs minus EB, so EB can be taken in the opposite direction. This will be the direction of EB. Remember, if Vs and EB, if they are on the same axis, then there will be no angle difference between them. But if the rotating magnetic field leads the rotor by alpha angle, which is natural, which is going to happen, so EB will be alpha degree lagging. So this is the EB case, this is EB, and here there will be alpha angle deflection. The magnitude of EB depends on the magnitude of the flux produced in the rotor side. If we increase the value of IF, or if we increase the excitation, the magnitude of EB will be increased. And the alpha parameter depends on the load. If we increase the amount of load, then this deflection will be increased, as we saw from these two figures. So this is plus EB. If we want to draw the value of Vs minus EB will be in the opposite direction. This is minus EB. So Vs plus minus EB will give us the value of ER, which is equal to Is into Xs. So if we want to draw the summation of these two vectors, Vs plus minus EB, that will give us the value. This is the summation of this Vs minus EB, and this is the value of Is into Xs, which can be denoted by ER. As this is alpha angle, this angle will also be alpha, which is the torque angle. And the value of Is can be figured out from 90 degree apart from this ER value. So this is the value of Is, because whatever the current that will go through this, the angle difference between the voltage dropped here and the current will be 90 degree. Current will be 90 degree lagging from this voltage drop here, as it is purely inductive we are considering. Next, we'll see effect of changing load on a synchronous motor. We know from our previous lectures that even though we change load, this load on a synchronous motor, the speed of the synchronous motor will not be changed as long as the rotor is interlocked with the rotating magnetic field. The speed will remain constant. So what is the effect of changing load on a synchronous motor? There is no effect on speed, but what happens to the current and other parameters? This is current Is passing through the stator side. Now we know the vector diagram. Let's draw a vector diagram with bigger dimension. This is Vs, supply voltage, and initially suppose the motor was having a back EMF. This is minus EB value with this amount of torque angle alpha. Now if we know this Vs and minus EB, from here we can figure out the value of the ER. So if we draw a parallel line from here to here, that will also give us the value of minus EB. This is minus EB, and Vs plus minus EB will give us the value of ER. This is ER, which is equal to Is into Xs. Now if it's ER, the 90 degree apart from this ER will give us the value of Is. This is the supply current. So the angle difference between the supply voltage and the supply current is theta, and that defines the power factor angle. Now if we increase the load because we are seeing the effect of changing load. For the time being, we are increasing the load. If we increase load, the magnitude of EB will not be changed, because we know the magnitude of EB depends on the flux produced by the rotor side, and flux produced by the rotor side depends on the excitation in the rotor side. As we are not changing excitation, we are changing only load, keeping other parameters fixed, so the magnitude of EB won't be changing. But whenever we will be changing the load, the angle alpha will be changed. If we increase the load, as we saw from our previous lecture, if we increase the load, then the value of alpha will also be increased. So if we want to have the same magnitude, we need to draw a circle considering this as the center to have the same magnitude. So the value of alpha will be increased for this case. This is new alpha. Let's name it alpha 1. So if this is alpha 1, what is the new value of ER? Let's draw it here. The new value of ER can be found out by drawing a parallel line of this green one from here. So this is the new value of ER. So ER1. So from here, if I take the 90-degree apart line, we'll get the value of IS. This magnitude of IS will also be increased. The magnitude of IS will also be increased because ER is increased as XS is fixed. So the magnitude of IS will be definitely increased. So what's happening here? This is my new IS1. So if we increase the load, we can see the current flowing through the stator side is increased, and the power factor angle theta1 is also increased, and the power consumption, initially this was the real power consumption, Vs Is cos theta, and the reactive power consumption was Vs Is sin theta. We can see the cos theta portion is this and the sin theta portion is this. Initially this was the case, but once we increase the load, what happens? The real power consumption also increases. This is the real power consumption for the higher amount of load, and this is the reactive power consumption. We can see both the real power consumption and the reactive power consumptions are increased. We are considering the Is cos theta only because Vs is fixed. So the power is defined by Vs Is cos theta. So Vs Is1 cos theta is greater than Vs Is cos theta. So we can say real power consumption increases and reactive power consumption also increases. Similarly, if we reduce the load, then alpha angle will be decreased. Having the same magnitude of EB, this line will come here. When this line comes here, if we draw the vector in parallel with this, so we can get a vector here. This is also minus EB. So the ER value will have this magnitude. This is new ER. This is ER2. 90-degree apart from this red one will give us this value. So we can see this IS2 decreases. The magnitude of IS2 decreases. Why? The total ER2 is decreased, so IS2 will also be decreased. So the real power consumption decreases and reactive power consumption decreases. So in a nutshell, if we say what is the effect of changing load on a synchronous motor, if we change the load on a synchronous motor, the speed of the motor won't be changing. But if we increase the load on a synchronous motor, the current consumption of that motor will be increased. We can see initially current was Is, then next after increasing the load it becomes Is1, so current consumption increases. Real power consumption also increases and the reactive power consumption also increases. If we decrease the amount of load in the motor, the current consumption decreases, the real power consumption decreases, and the reactive power consumption also decreases. And this is natural. If we load the motor with higher value, the current consumption will be higher. the current bill will be higher. If the motor is lightly loaded, the current consumption will be lower and the motor will be running consuming lower amount of powers. Next, we'll see the effect of changing excitation, that means field excitation, on a synchronous motor, considering we have a constant load connected with the motor. Load is not changing, the excitation, field excitation in the rotor side is changed. As I said earlier, whenever we'll change the excitation on a synchronous motor, the magnitude of EB will be changed. Now here we need to consider another thing. Suppose this is north pole of RMF, rotating magnetic field. This is the south side of the rotor. We have angle deflection between them is alpha. Now, if we increase the excitation in the rotor side, what will happen? This field strength will be higher. If we increase the excitation in the rotor side, that higher field strength will increase the magnitude of EB, that is true. Also, that higher field strength will decrease the value of alpha. Why? When we will have the field strength with higher value than the previous case, they will try to hold each other for the same amount of load. They will try to hold each other more tightly and the value of alpha will be decreased. So whenever we are increasing the excitation, the magnitude of EB will be increased as well as alpha value will also be decreased. Now let's draw the vector diagram. This is Vs. Suppose initially the value of EB was this. This is minus EB. And this is the case for ER, which is equal to IS into XS. This is load angle alpha, and 90 degree apart from this we will get the value of IS. Now remember one thing, unless or until we increase the load, the real power consumption of this motor won't be changing. The real power consumption only changes when we change the real load. As long as we are not changing the real load, we are changing only the excitation, the real power consumption, which depends on IS cos theta, this is the theta, IS cos theta, this value will remain constant. Now if we increase the excitation, as I told you earlier, the magnitude of EB will be increased and alpha will be decreased, and that will follow this line. So after following this line, if I extend this line here, this is the new EB, suppose minus EB1 after increasing the excitation. So the angle is decreased, alpha 1 is less than alpha value, alpha is decreased, but the magnitude of EB is increased, and corresponding value of ER can be found out from here. So this is the value of ER 1, and the current IS can be found out, and this current will follow this vertical line. Why? If it follows this vertical line, then IS1 cos theta, this is IS1 cos theta remains same, and the real power consumption remains same because we are not changing the load. As we are increasing the excitation, what's happening? The real power consumption remains same, Vs IS1 cos theta equal to Vs Is cos theta, both are same, but initially the reactive power consumption for the previous case was Vs Is sin theta. Now this is theta 1, this will become Vs Is1 sin theta 1. So this reactive power consumption is lessened. This is very important feature. By increasing excitation, we can improve the power factor We can see initially power factor was higher than this theta 1 case. If we increase the excitation, theta decreases and power factor improves. If we keep increasing the excitation, at some moment, the value of EB, for example, if we increase excitation a bit more, from here, if we draw the parallel line of minus EB, this is minus EB2, so this is ER2, then the current IF will be on the top of this VS. You can see we are getting unity power factor. This is IS2, and a synchronous motor can be run with leading power factor. If we can run a synchronous motor with leading power factor, this motor can be used as power factor improvement device. So if we increase the excitation further, suppose we are increasing the excitation further, what will happen? This is for the case minus EB3. So if we draw a parallel line from here, this is minus EB3. So VS minus EB3 will give us the value of ER3, and 90 degree apart from ER3 will give us the value of new IS. This is IS3. We can see the supply current IS is having the leading theta 3 value from VS. So under this condition, overexcited condition, we can say we are giving very high excitation. The motor can be run with leading power factor. When the motor is run with leading power factor, this motor can be used as power factor improvement device. Generally, we use capacitor bank for improving the power factor. Synchronous motor with higher excitation that takes leading current can be used for that purpose as well. Thank you for today.